We are here to talk about evidence for evolution.
Yes, Lorraine, and I hope that the learners tonight, whoever's present here, will enjoy this and also have a better understanding, because as scientists we're constantly looking for evidence as verification for what we're always looking for.
Yes, that is what scientific investigation is all about. And although we can't go and do experiments on most of the evolution, the evidence that we have, we can at least investigate. And yes, sometimes people say, yeah, but how do you prove evolution? What proof do you have? And although we don't run around for proof all the time, we don't have to justify, what we have is more than enough evidence to show you that evolution indeed did take place and still is continuing today.
Yeah, and as they say that the fossils, they really tell a story. So, and I think we'll be kicking off with paleontology,
Yes.
which is the story about the fossils.
Okay, so let's have a look at our slides. When we talk about evidence for evolution, there are 5 main components or aspects to evidence for evolution. The first is paleontology, and as Colin has said, that is about the fossils. Then we have comparative anatomy, comparative embryology, comparative biochemistry, and biogeography. So these are the 5 aspects that we will discuss tonight. And let's start off with paleontology, or fossil evidence. Now, I'm not going to go into detail about all these terms, because you should know by now what they mean, and you should be able to use them and to explain them. Paleontology is the study of fossils, and the paleontologist is the scientist that studies fossils. Remember, we did that last week and the week before, Colin, what fossils are. So the remains or the imprints or the traces of organisms that lived a long time ago that are preserved, and usually in rocks. Fossilization and the fossil record. Let's continue from there. Fossil records. Now, at this stage, grade 12s, fossils are the main sources of information about animals that lived a long time ago and that are now extinct. But it's important that you remember that just about 0.1% of all organisms formed fossils. And that is not just as far as numbers are concerned. You must remember that there are many species that we will never know about simply because they weren't suitable, and they didn't contain suitable material for fossilization, or they didn't die in suitable circumstances to fossilize.
And you know, Lorraine, that is so important, that what you just said now, en ons wil dit tog beklemtoon, dat leerders moet weet waarom dit dan is dat daar so 'n klein persentasie van organismes is wat nogal ooit gelewe het, wat fossiele gevorm het. En onthou wat Lorraine gesê het, want dit is baie belangrik, dat die omstandighede of die toestande vir 'n fossiel om te vorm moet natuurlik gunstig wees, en dan ook dat baie van die organismes het nie geskikte materiaal om 'n fossiel te kan vorm nie, want ons gaan later kom by die fossileringsproses, watter organismes wel geskik is om fossiele te kan vorm.
Ja, en as julle dan nou wonder, hoekom doen ons dan nou weer eens fossiele, hoekom praat ons weer eens oor fossiele, dan is dit omdat ons nou uit 'n ander perspektief daarna kyk. We've already discussed fossils, how fossils form, what they are, where we find them. But now we are looking from a different perspective. We now look at fossils as evidence of evolution. Right, let's go back to our slides. Fossils give us the opportunity to study and to compare. If we look at this picture, for instance, this is now the now very famous fossil of Archaeopteryx that is regarded as a transition fossil between reptiles and birds. And at the top there is an artist's idea of what the true Archaeopteryx might have looked like. We don't know about the colors really, we've said that before, but you never know. This might have been, and we can deduce this by studying the fossils. This is something that by now I hope you know off by heart. What are fossils? I've referred to that earlier. Colin, I don't think we need to dwell on this.
Yeah, I don't think so.
Right.
I don't think learners should have a problem with the process of fossilization either, but we can just run through that too.
Yes, and there you have 4 bullets. Those are the requirements. Colin said earlier, she talked about how few animals actually, or plants for that matter, actually fossilize. And it is because these 4 requirements are necessary. Low temperatures, little or no oxygen, so that there is no decomposition, and there should be a possibility of being covered by sediment. Now, sediment, sand or mud, and that's why you often find fossils in areas that used to be flood plains, for instance, river banks, river beds, inland seas, for instance. It is because it was covered by sand or by mud that over time hardened into sedimentary rock, and over long periods of time, changes in the Earth's surface might have brought these fossils closer to the surface. And then erosion, earthquakes, rock blasting for building and with mines. You would be surprised how many fossils have been discovered where people started digging or blasting rocks because they wanted to build something. And then they would find a fossil, and they would first dig out all the fossils, and excellent opportunity for fossil hunters then. Different types of fossils. This is all revision, we've done that. Body fossils, so where complete organisms are preserved in ice or in resin, or parts of the organisms, for example, shells. Remember, resin is the hardened gum of trees. Ice. Just something, Colin, that learners should remember is that we get different types of mummies. We get naturally formed mummies. For instance, a body that was preserved in ice for thousands of years, or in a desert, dried out by the dry desert air, blown, covered by sand, and then uncovered after many years. And they are body fossils. But why can any of the learners guess why we can't regard the Egyptian mummies as fossils? Because we call these body fossils, we often call them mummies. But why not Tutankhamun and his friends? Why do you think the learners know? Simply because those mummies were done with human intervention and with special processes and special chemicals. So that's why we don't regard them as true mummies. Then we have the casts, or the molds, and the trace fossils. Just for interest's sake, what I've got here is a photograph of a coprolite. Can you remember what a coprolite is? It's a fossil of feces. And why would that be of any interest? Because we can see what the animal ate. And from that we can deduce whether the animal was a herbivore, a carnivore, an omnivore, even something about the vegetation, other animals living there, and even something about the climate. Because certain plants need a certain type of climate to thrive.
And maybe before we just go on to the next slide, we can also, Lorraine just asked why we don't see the mummies of the Egyptian mummies as fossils and regard them as fossils. You must also remember anything less than 10,000 years, it takes at least 10,000 years for a fossil or for an organism to fossilize. So anything younger than 10,000 years is not a fossil.
In other words, you would say anything younger than 10,000 years would really be a job for the anthropologists to study. Good one tip that. Thanks, Colin. There's just pictures of the different types of fossils. We have referred to some of them before. This is just to recap. A body fossil, a trace fossil, there's mineralized bone, and there's a mold, right, or a cast. That's of a leaf. And quite often we don't have actual mineralized leaf fossils, but we do have the casts. Right, now this is where we want to be now. Why are fossils important to us as evidence of evolution? And simply,
now if you look at the uses of fossils, what can we use fossils for? First of all, it gives us somehow an idea of what life was like previously, and it gives us somehow an idea of evidence of what life was like on Earth. You remember, Earth, as we currently know, is about 4,600 million or 4.6 billion years old. So, how do we know that? We look at fossils and we can see at the time what happened. So it gives us also an idea of the progressive changes, how animals or plant groups have changed over millions and millions of years. It also gives us somehow an idea of what we have found, but also the age of the different strata, the geological strata. And also, like Lorraine said, why did we look at the feces? To see what certain organisms ate at the time, to see whether they were herbivores or carnivores, but also, if we find certain fossils and we find even pollen and things can fossilize, it gives us somehow idea of the type of climate and the environment if we study these fossils to see what has happened and what has caused these changes. So yes, we can use fossils for quite a few other things too, but these are the most important things, and you must also know this for exam purposes. If we look at, can we really date fossils? Now we get different ways of determining the age of fossils. If we say we date fossils, I don't think the fossils will go out on a date, but we look at the age of the fossils. Now this one here is referred to as relative dating, and this is exactly what Darwin has seen on his 5-year journey. Now if you look at the fossils that you find at the bottom strata, then you can say, right, these fossils, they are much older than these found right on the top layer, and the youngest fossils we will find at the most upper layer. So this is called or referred to as relative dating. So we don't have an exact age or date, but we can at least say that those that we have found at the bottom, they are much older than those at the top. Absolute dating. This is a bit more difficult because we refer to the radiometric dating. Now, radiometric dating, we talk here, some of you might have heard of these, but we use isotopes. And Lorraine, if we can just explain to them what isotopes are.
Yeah, this is quite an interesting aspect, and people often say that you cannot date a fossil, and you don't know, and that radiometric dating is not exact. But we get different types of radiometric dating. They use uranium, thorium, carbon. There are many elements that are used for radiometric dating. Now, maybe those of you who take science will know what we're talking about, and if we can have the paper, then I can explain to you how carbon dating works. Now, carbon is an element, C, that has two types of isotopes, carbon-14 and carbon-12. Now, carbon-12 is the usual condition in which we get carbon, the non-radioactive form. And this means, people, that in the nucleus, under normal conditions, in the nucleus of carbon, there are 6 positive particles called the protons. And around different levels, or energy levels as we call them, a little bit of science. Oh, there's one too. Actually, you've got 6 electrons. So this is a neutral atom. But now, also in the nucleus, you have neutrons, neutral particles. Now, you take your 6 and subtract it from the 14 or the 12 to see the number of neutrons. Now, 14 minus 6 will give you 1, 2, 3, 4, 5, 6, 7, 8 of these neutrons. Now, carbon-14 will emit radioactive radiation. And radioactive radiation actually changes the structure of the nucleus and gets rid of 2 of these neutrons so that you won't have 12 nucleic particles, but 14, but only 12. Now, if this sounds very technical, please sigh with relief because you don't have to know it. But the physical science people will now know exactly what we're talking about. As long as you remember that a more radioactive form called carbon-14 was changed into a non-radioactive form, carbon-12. Now, the change takes a certain time. If I have X amount of carbon-14, after a certain amount time, I will have X divided by 2. After a certain time, I will have X divided by 2 divided by 2. And this is what the picture on, if we can look at the slides, what this picture is trying to tell us. After a certain time, if this lady with the racket, the parent, is our carbon-14, after the first half-life, in other words, the time that it will take half of the amount of carbon-14 to change into carbon-12. This is little carbon-12 and mummy carbon-14. After the first half-life, half of mummy will remain. The rest of mummy turned into carbon-12. After the next half-life, half of mummy would have disappeared and changed into carbon-12. And another half. Can you see? Next time, if we had another picture, only half of this picture, in other words, a quarter of mummy's head, would have remained. And this tempo of radioactive decay for each element is a set tempo. So if you can look at the ratio of carbon-14 to carbon-12 now, you know the tempo, you can work out how long it has taken. Met ander woorde, Colin, as ons weet hoeveel koolstof 14 ons vandag op aarde het, wat is die verhouding tussen koolstof 14 en koolstof 12? En ons kan gaan terugkyk na ons materiaal en ons kan daardie verhouding kyk deur ons halfleeftyd te gebruik en die tempo daarvan kan ons dan vasstel, goed, dit het so lank moes dit geneem het om vir daardie hoeveelheid koolstof 14 om te verander na hierdie hoeveelheid koolstof 12 en die verhouding om nou so te wees. En dan kan jy die ouderdom bepaal. And it's not exactly to the morning or the afternoon of a certain date, a certain year. Give and take a few thousand years in many cases. But I mean, what are 1,000 or 2,000 years in comparison with 3.5 billion? Okay. That, I think the next one, Colin, will give a better idea, scientifically.
If we look at this scale too, here we have, for instance, and there are many other ways of showing this, but what you have to know is that if we can go back, there's an original form of any isotope. And normally, say for instance, this is uranium. And it takes a certain amount of time, and that time for half of this uranium isotope to decay to the daughter isotope, which is normally lead. You see, so uranium is the radioactive isotope, and the lead is the non-radioactive isotope. And the amount of time that it takes is a fixed time. So dit is 'n vaste tyd wat dit neem vir Iran om te verweer na lood. En dit is 'n vasgestelde tyd en vir alle isotope neem dit presies dieselfde tyd om te verweer na die dogterisotoop. And that is what you have to know. You see, you don't have to know the specific things, but if you look at this, here you have the mineral at time of crystallization. You see, this is the parent isotope. Half of this, sien jy, die helfte daarvan, dit neem, kom ons kyk, hierdie is 50% van dit, so die helfte van dit gaan dan verweer na die dogterisotoop of element. En dit staan bekend dan as 1 halflewe, 1 half life. And then, die ander helfte sal jy hier sien, van die oorspronklike, gaan dan presies dan ook weer dieselfde tyd neem om te verweer na die dogterisotoop, en ons praat van 2 halflewens, en so kan ons aangaan. En dit is hoe hierdie ouderdom van rotse bepaal kan word. Let wel, fossiele word gevind in sedimentêre gesteentes, maar dit is gewoonlik die ouderdom van radioaktiewe materiaal, en dit is stollingsgesteentes. Just remember, it's igneous rock that you can determine the age of, and not the sedimentary rock.
En hier's 'n vraag, Karen, oor hoekom ons so lank hier by stil staan. Julle kan 'n vraag hieroor kry, uiteraard. Maar onthou, dit gaan oor bewyse van evolusie. En leerders moet weet hoe ons hierdie meganismes, metodes gebruik om sekere inligting oor evolusie agter te kom. Hier was ook 'n vraag, en dit is nogal 'n goeie vraag. Gestel nou maar daar's 'n aardbewing of een of ander opwelling wat maak dat ouer fossiele nou bo-op jonger fossiele lê. En dit kan gebeur, dan kan jy mos nie sommer die aanname maak dat die boonste laag bevat die jongste fossiele nie. En dis hoekom ons ook nie verlaat net op een metode nie. Met ander woorde, if you find that a fossil was moved and that you had a change in the different layers of the arrangement, this is also where radiometric dating can be of benefit.
Ja, ek dink dan gaan ons seker ook nie gebruik maak van daardie tipe metode nie.
Ja, onthou, elke metode word gebruik vir 'n geskikte tipe fossiel en 'n tipe ding. Nou goed, kom ons kyk verder na ons skyfies. Ons is amper klaar oor fossiele gepraat. It is very important that you also remember that the presence of certain fossils also give us an indication, and it also serves as proof of the theory of plate tectonics and continental drift. And we have referred to this before. But at this stage now, we're putting emphasis on it to tell you what proof of evidence we have for evolution. The fact that we have similar fossils or the same fossils on different continents that are not connected today. En ons het al in detail bespreek wat hierdie skyfie beteken, maar leerders moet dus nou weer net onthou. Goed, kom ons gaan aan. Ons is nou klaar met fossiele en paleontologie as bewyse van evolusie, en nou gaan ons kyk na vergelykende anatomie. En dit het ons ook al reeds tot 'n mate na verwys, maar ek dink ons gaan nou heeltemal op 'n ander manier kyk. Karen, ek dink is baie belangrik dat die leerders nou bybly hier.
Ja. If we say this is a pentadactyl, then we say it is a 5-digit limb. If we look at the limbs, you have the forelimb and the hind limb, and they just have different names. If you take the forelimb, you have the humerus, die boarm, you have the radius and ulna, die radius en ulna, die carpale beentjies, metacarpale beentjies en die phalanxe. So there you have the forelimb, the hind limb, of course, you have your femur, the tibia and fibula, the tarsals, metatarsals and phalanges. En dit is wat bedoel word met hierdie 5-digit of die pentadactyl ledemaat. Now why is this, how can we compare or take this? And this similarity of structure we refer to as the homology. So we look at homologous structures, homoloë structure. What are homologous structures? Homologous structures is that we have different organisms that contain all these 5 different limbs, and all of them must, because they contain this, we say they must contain, or it's indicative of a common ancestor. For instance, there you have your 5 digits. You take your arm, a human arm for instance, here and there you have a different an elongation here and there, and a shortening here and there. And what do we have? We have a bat wing. Or there we have some fusion, sien jy? Ergens is daar dan nou die samesmelting en hier en daar 'n verandering, maar die 5 dele steeds daar en ons kry die per 'n voël se vlerk.
Jy het jou nou amper sleg verspreek,
O, ja.
Karen, met 'n perdevlek. Maar mense weet nooit nie, dalk as ons met Pegasus. I think it's important that learners remember when we talk about the digits here, these are the digits, right? So it's a pentadactyl limb is a 5-fingered limb. Go and look at some others and you won't find 5 fingers or 5 toes. But if you look at these, I think this is an excellent picture.
I think it is. Here you have, and this is actually where we compare. Hier vergelyk ons nou die verskillende voorarms. Hier is die mensen. Kyk na, as jy nou nie die ander gedeelte van 'n akedus het nie, sien nie, jy sal nooit kon dink dat dit 'n akedus se voorarm is nie, of 'n katsin, 'n walvis, 'n vleermuis, of 'n padda en 'n voël. But look at that. There are so many similarities that is actually it's frightening if you look at that. And this is where we look at that. Or can we go back? Is there something else that you would like to say?
No, I just wanted to say is that learners, before we get to the analogous or the analogous structures, is that learners must be able to recognize in a modified limb which is the humerus and which is the femur, which is the radius. So go and practice. We're not going to expect you to throw you with pictures and you must identify the type of animal. I will tell you, or the examiner will tell you, this is a mole, which I'm not, by the way. This is a mole, or that is a bat, and you have to be able to identify the different types of bones.
I think what is important, if you can just go back to that slide, what is really important for learners to understand is that here you have limbs, they all look similar, but they all have different functions. You see, here we can do very complex things with our human hands, whereas a lizard can't do that. They mostly use it for running. A cat, for instance, can jump, whales swim, bats fly, frogs can jump and swim, and birds, they fly. You see, these are homologous structures. They all have different functions. But what is important, because of the pentadactyl limbs that we have and we all share, that means that we share one common ancestor. And I think that is important. So if we look at analogous or analogous structures, there we have the fins of a shark, the flippers of a whale, and we can also look at the wings of a bird and the wings of a butterfly. Why do we say these are analogous structures? You see, they use it basically to do the same thing. They swim with those. But the one has fins and the other one has flippers. Here the wings of this eagle is used to fly, as well as the wings of an insect. But what they don't have, you see, if we go back to homologous structures, they all had different functions, but they shared one common ancestor. Analogous structures, they have a common function, but that does not mean that they come from the same or share the same ancestor. And I think that is important for you to understand and to differentiate between the two.
Especially if you go and look at the basic structure of these organs and the development, embryonic development, and all of that. I mean, I think it's very easy to see that a butterfly wings and an eagle wing or bird's wing are two totally different things. But with the fins and flippers of fish
Yeah.
and whales, learners might think there are similarities, but only superficially, yes, but not with basic structure, and that is important.
And exactly, and for exam purposes, they must remember. I think to compare the
Yeah.
two is very important, and especially if they ask you to table this, there you have a table just to compare homologous and analogous structures. Here you see homologous structure or organisms. They share common ancestor. Analogous, they don't share a common ancestor. And then, of course, they have the same basic structure. We refer to the pentadactyl limbs, and the wing of an insect. It differs completely from that of a bird. And of course, homologous structures, those were adapted for different functions, as we have pointed out. The bat flies, the bird flies, but a whale swims, and we can do very complex things, whereas all the wings are meant to fly, and the flippers and the fins are made to swim with. And this brings us to where Lorraine will just explain to you what is meant with divergent and convergent evolution.
Right, divergent means to spread out. If we can have a look at the paper here. Divergent, yeah, I think they can read. Divergent means to spread out into different directions. For instance, we have our common ancestor with the basic structure of the limb. And we've got the bat and the bird and let's say the human and let's say a mole. Each with the same basic structure, but because of different needs, because of different environmental conditions, the evolution of that limb went into different directions. Convergent means to come together. You've got two totally different things. You've got a bird with its wings, and you've got an insect with its wings. They are totally different. They are not that closely related. They developed different structures, but because they have a common need, and because they have to survive in the same conditions, they developed the same structure. So divergent is spreading, convergent coming together.
And I think that should explain it to them.
Right, what's our next slide, Colin?
Reg, en miskien net vir die Afrikaanse leerders as ons kan sê dis divergerende evolusie en konvergente evolusie.
Ja.